Okay, hello everyone. Quick follow-up to class on Monday, and I suppose Tuesday we won't get to this either. This is actually the most important thing from post-FTC day, and it's the following. Integration by substitution. Now, if you take a sort of bad perspective on this, then this is actually barely a new thing. Here I have an integral. The integral is from pi over 4 to pi over 2 of 2 cosine 2x dx. How am I going to do this? Well, the thing about doing integrals now is it's easy if you know an antiderivative. So it seems that the problem of integrating this function, of computing this integral, is as simple as finding an antiderivative of this function. Okay, so that is a way to do this. And so here I'm gonna mention option 1. This is an option, but I think it's a bad option, and it's so I'm gonna teach it first. And it's the thing that you would all just do if I didn't tell you otherwise. And that is you would just anti-differentiate. You say, okay, I see that there is a function here. This function is 2 cosine 2x. Hey, can I find an antiderivative of this? So let's go. So option 1 says, first, let's compute the antiderivative of 2 cosine 2x. Okay, and now, well, let's see. How do we do this? It turns out that we know how to do this problem. Why do we know how to do this? Because we've been practicing this for 3 weeks now. You could almost just do this in your head, but to sort of prove a point or something, I will go through the actual substitution. The substitution here is to let u be 2x. So if I let u be 2x, then I differentiate both sides, and du dx is 2, and therefore du equals 2 dx. And okay, the 2 dx is actually just sitting right there already, so everything is more or less just perfect as is. Therefore, returning to this problem, I convert everything to u's, and I see that this is just the antiderivative of cosine u du. So I've simplified my life by doing this substitution. What is the antiderivative of cosine? Well, it's sine. So the answer to this is sine u plus c, because the derivative of sine is cosine. And finally, u is 2x. So sine of 2x plus c is the actual answer here. And let's see, I'm kind of worrying about my space. Okay, well, anyway, all of this becomes a kind of side calculation that we have just done. So in other words, we've successfully, and you probably could have even done this faster with less work shown, we've successfully anti-differentiated this function. And now, returning to the problem at hand, what is the integral from pi over 4 to pi over 2 of 2 cosine 2x? Well, I say that it is, according to the fundamental theorem of calculus, it's just sine 2x, and that's going to be evaluated at pi over 2 and pi over 4. And the answer to this problem is therefore, well, when you plug in pi over 2, you get sine of pi. Well, I guess I could even just write it, right? It's sine of pi minus, when you plug in pi over 4, sine of pi over 2. And then that's just 0 minus 1. So the answer to this problem is just 1. All right, so that was, maybe that was so easy and so straightforward and so obvious that you might be thinking, why do anything else? Yeah, though it's possible in this case to do it this way, there's a kind of a better way, and I'm going to try to convince you that this way is better. Okay, well, anyway, let's go. What is option number 2? Option number 2 is, instead of taking this detour into anti-differentiation, let's just perform our substitution on the integral itself. So this is integration by substitution, which really is kind of a separate thing, although it's very closely related. All right, what do I mean by this? Well, I have now pi over 4 and pi over 2. And, well, what are we going to do? We're going to, okay, let me just finish rewriting the problem. It's 2 cosine 2x dx. And now I want to, once again, I want to simplify things by performing a substitution. But here, I'm going to just perform the substitution directly on the integral. And by that I mean, well, okay, it's in fact the same substitution, u equals 2x. So I still want that to be u. So I'm going to say, yeah, let u be 2x. And yeah, okay, it's really the same thing as we've been doing, but I just want to now do something that I haven't done yet, which is really think of u as a function. It's a function which takes an x and outputs, double that number. So, okay, so this is just kind of just a slightly different way of writing what we've already been doing now for several weeks. And now what I really want to do is, well, okay, once again, right, du dx, which is also known as u prime of x, is 2. And so it's still true that du equals 2 dx. And so, okay, everything is actually just exactly the same. But now, when I go to apply this substitution, I'm going to apply it directly to the integral. And I'm going to say, okay, well, once again, I have 2 dx just sitting here. And so I'm just going to replace everything with u's. So instead of cosine 2x, I'm going to write cosine u. And instead of 2 dx, I'm going to write du. And now I have to kind of think for a second. Because, and here is the sense in which I think it's helpful to think of u as a function. Because really what we're doing when we, so we're switching variables is all we're doing, right? And we're switching variables. We're letting u be 2x. What that really means is for any x value, the corresponding u value is twice as much. So that's why this is kind of like a function. Okay, and now I have to look at these numbers, right? Here's the crucial moment. What are these numbers? Pi over 2 and pi over 4. Pi over 2 and pi over 4 are x values. They say where on the x-axis do I start integrating and where on the x-axis do I stop integrating. But I have now rewriting this function in terms of a new variable. And so if I'm rewriting in terms of a new variable, then this number here, pi over 4, is not the appropriate number anymore. Because when x is pi over 4, u is pi over 2. In other words, I'm going to plug in pi over 4 into this function to convert the x value, pi over 4, into the corresponding u value. And once again, we plug in u equals pi over 2. And if we do that, then what do we get? Well, what is the u function? It's just a function which doubles. And so this whole thing becomes, well, u of pi over 4 is just pi over 2, and u of pi over 2 is just pi of cosine u du. And now, what I have really done, unlike on the left here, what I've really done on the right is I've performed my substitution sort of directly on the integral. In other words, I don't look back. I've rewritten this integral in terms of a new integral involving just u's, and now I simply do this integral. So what is the integral of from pi over 2 to pi of cosine u? Well, the antiderivative of cosine is just sine, and so this whole thing becomes sine of u evaluated at pi and pi over 2. And what is the answer? The answer is sine of pi, which is 0, minus sine of pi over 2. Have I messed up over here? I did mess up. Sorry. 0 minus 1 is negative 1. Sorry about that. Good thing I am doing this problem twice. And over here, I also get negative 1. Okay. So, all right. Whoa, what just happened? This might almost seem like some kind of minor cosmetic difference, and in some ways, maybe it is. Let me kind of explain this whole process. Okay, I crammed everything in here so I'd have enough space. So what is really going on here? So I'll try to explain kind of like, geometrically or something. So first of all, what's the big, let's start. What does this 2 cosine 2x function look like? Let me write this as y equals 2 cosine 2x. Well, I just know this function. It's a famous function. I know what cosine looks like, and the 2 is going to smush everything by a factor of 2, and the leading 2 over here is going to stretch everything vertically by a factor of 2. So what do I have? I have a function which has been stretched vertically by a factor of 2, and which also has been smushed horizontally by a factor of 2. So now this will be pi here, and okay. Now I just draw cosine. What does it look like? That's pi over 4. That's pi over 2. That's 3 pi over 2. And the cosine function is going to be like boom, 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 boom. that is an entire period of this cosine function. And now, what integral is being computed here? The integral from pi over 4 to pi over 2. So let's draw it. It's going to be all this. And all right, I think I have a kind of a geometric understanding of why this integral is -1. Because the big thing that we did, maybe I'll squeeze it over here in the corner or something. The big thing that we did in class today was to talk about how one hump of sine has area 2. So if one hump of sine has area 2, then of course one hump of cosine also has area 2. Cosine is just sine smushed over. But now, what can I say about this function? Well, this function is going to smush everything horizontally by a factor of 2. So everything's going to have half as much area as normal, but then it's also being stretched vertically by a factor of 2. Therefore, the area gets doubled. So I claim that one hump of this 2 cosine 2x function is also going to be 2. And therefore, half a hump, which is what's being depicted here, should be 1. And because it's -1. So here, to me, I'm like very confident that all of this math, if I is going to sort of give me -1. That's kind of the answer that I expect. So I'm feeling kind of good. But notice that here, what we have is, maybe it's better not to call this y, but to call this, like, give this function a name or something, like, you know, call it f. And then, because what do we really have here? This is the x-axis. What is the x-axis? It's the set of numbers which get plugged into sort of this function. They're x values. And so where do I start integrating? I start integrating here at pi over 4, and I stop integrating here at pi over 2. So you have to sort of feel that pi over 4 and pi over 2 are the x values. They're the lower limit of integration and the upper limit of integration for this function. Okay, but what have I done? Over here is in this option number 2, I transformed this integral. How did I transform this integral? By creating a new integral. And the new integral that I created is this one. And okay, I can also draw a picture of this. What is this function? Well, it's the cosine function. But now, going sort of out, maybe I'll only go out to pi so that these like kind of match up nicely. Here's pi over 2, here's 1, and maybe it's a little bit higher than that. Maybe it's like up here. And okay, it's just regular cosine, yeah? So it's like jom, jom, jom. And so what we get is something that looks like that. And here we go, right? It's this area now. Okay, and so it all kind of just makes sense, right? Here we have a new function. This function g takes u values and outputs cosine u. And does everyone kind of, hopefully everyone watching this understands that what's in fact happening is like this geometric transformation. I've converted, the point of this whole conversation is that this integral gets converted into this integral. How do we convert this integral into this integral? By performing a sort of variable transformation. I change every x value to its corresponding u value. And when I do that, I get this kind of new function, which is the cosine function. And now, whereas before I was integrating from pi over 4 to pi over 2, those are not the appropriate bounds anymore, because those were the x values of where I start integrating and stop integrating on the x-axis. But now I'm on the u-axis. And of course, if my transformation is to double every x value, then I also need to double the starting point and the ending point. So instead of starting at pi over 4, I start at pi over 2. And instead of ending at pi over 2, I end at pi. And you should feel, of course, that this is also going to be kind of obviously -1, because now it's just half of a hump of cosine, which has area 2. Okay, and so the moral of the story is that it's just easier and simpler, instead of taking a detour into antidifferentiation, to simply just do your substitution on your integral. But when you change the function, you have to also change the upper limit and lower limit of integration. All right, that was perhaps a little bit too long-winded. Let's just go to one example problem, and then we'll stop. This is a pretty hard example, though, actually. So let's go. The integral from 1 to 5 of x over root 2x minus 1. How are we going to do this? Well, it seems that this is kind of a complicated function. And what I want to do is kind of make it simpler. And what I see is that, in particular, this 2x minus 1 is kind of annoying. I don't want that to be there. I wish that weren't so complicated. I wish that were simpler. And so I'm going to choose to perform a substitution. So I'm going to let, I'll do it over here, I guess. I'm going to let u be 2x minus 1. But now, thinking about this a little bit differently, of course, this is optional to write this, but I want to encourage you to think of u as actually like a function, which takes as input x values and takes as output u values. And now this function, is some kind of transformation. And I'm transforming everything. That was the point of this whole geometry on the previous page, is that when you define this new function u right here, it's not just a simple substitution. In fact, what you're doing is you're transforming everything. You're transforming all the rectangles. You're transforming the function. You're stretching the function by some kind of a way. And you're also stretching the starting and ending point. Okay, so if that's the case, still though, the math is the same. Du dx is just 2, and so du is just 2 dx. And therefore, I see, going back to this problem, that I need a 2 here. And so I undo the damage with a 1/2 on the outside. Okay, what does this accomplish? Sorry, I see now that it's not just the 2 really is, it's here that the 2 belongs, right? 2 sort of next to dx or something. Okay, so now, what am I doing? I'm supposedly transforming this integral into a new integral in terms of just u. So I still have the 1/2. And down here, root 2x minus 1 becomes, of course, root u. That was the whole point. And then 2 dx is just du. And then now I have kind of a little bit of a hard problem, which is, what do I do with this x? Well, that's when you go back and you do one of these, swaparoos or whatever. If u is 2x minus 1, then that means that u plus 1 is 2x. Which is another way of saying that x is u plus 1 over 2. And so that whole thing gets substituted back in over here. So this becomes u plus 1 over 2. And sorry, handwriting's a little bit bad there. U plus 1 over 2. Okay, and cha-cha-cha. And the key moment here is that when we transform this integral into an integral involving x to a new integral involving u, I need to transform the upper limits and lower limits of integration as well. So that becomes u of 1 and u of 5. Okay, and so continuing on with this problem, what do I get? This looking kind of a little bit ugly over here, but this can be simplified. This becomes that 1/2 can come out, and I get 1/4 the integral from, what is u of 1? Well, here if you just plug 1 into the u function, you get 1. And if you plug 5 into the u function, you get 9. And so, if u is 2x minus 1, then the sort of transformation takes 1 to 1, but it takes 5 to 9. Okay, and then what do we have here? U plus 1 over root u. All right, so I just did a lot of work. Is this actually helpful? Is this actually easier? I think it is easier now, right? Why is this an easier problem to integrate? Well, this can be simplified now, right? It's very, very useful to have my denominator be a single term, because then I can split this up. So this becomes 1/4, the integral from 1 to 9 of u over root u is just root u. So that's u to the 1/2, and 1 over root u is u to the negative 1/2. Okay, so all that time last month when we were anti-differentiating, we were just getting really good at this kind of thing. So this you should have to sort of see in advance that this was going to be useful. Okay, now finishing it off. Now I apply the fundamental theorem of calculus, and I anti-differentiate u to the 1/2. What's the antiderivative of u to the 1/2? Up a power to 3/2, and you divide by 3/2. So this is 2/3 u to the 3/2 plus. And the antiderivative of u to the negative 1/2, you go up a power to 1/2 and you divide by 1/2. So that's 2, and then maybe go right for root u. All right, so there's still some work to do, but notice how I never go back, right? Here's the whole reason why this method is better. There's several reasons, but one reason is because once you do your substitution, then you just x is just gone forever, right? That's kind of the big takeaway here, is that I've now fully replaced my original problem with this problem now in green, and now I just push on forward solving this green problem. The value of this green integral is equal to the value of the original integral, and so I just solved this one. And so now I'm basically done. I just have to do some arithmetic. So what do I have here? I have 1/4 times, well, I plug in 9, and I get 9 to the 3 halves is 27. So I get 2/3 times 27 plus 2 times root 9 is 3. Minus what I get when I plug in 1, which is 2/3 plus 2. And so what is all this? It's 1/4 times, that's 9 plus 6 minus 2/3 minus 2. So that is, I hope this is all right. Let's see, 15 minus 2 is 13 minus 2/3. And yeah, what is that? Let's see, I guess I can multiply. Somehow this has gone wrong or something. 1/4 times 39 minus 2, 31/3. Sorry, something went wrong. I'm actually just like looking at my work. Sorry, 9, I plug in 9 and I get, this is all good. 2 times 3, 9 to the 3 halves is 27, so that's all right. Oh, that should be an 18 here. I see. So that's 16 and 6 is 22. 1 second. 27 times 2/3 is certainly 18 plus 6 minus 2/3 minus 2. Okay, so hopefully I fixed all those mistakes. So first that's 22 minus 2/3. And what is that? 66 minus 2, so that's 1/4 times 64/3. So that's 16/3, and that is in fact the right answer. Okay, so this was pretty hard. This integral was 16/3. What did you have to do to get this right? You had to do a substitution. You had to do a lot of this kind of like backwards move, plug it all in, and then just crank it all out. All right, good. How long was that? Like 25 minutes or something, I fear. Yeah, 22 minutes. Okay, not too bad. Bye.